CPU task scheduling is the fundamental process that determines which task gets to use the processor at any given moment. This critical operating system function ensures maximum CPU utilization while maintaining system stability. Think of CPU scheduling like a classroom where a teacher calls on students to answer questions. Just as only one student can speak at a time to avoid chaos, only one task can use the CPU at any moment to prevent system crashes. There are several algorithms that operating systems use to decide which task runs next. These include first come, first served, shortest job first, round robin, and priority scheduling. Each has different advantages and use cases. First come, first served is the simplest scheduling algorithm. Tasks are executed in the order they arrive, just like a queue at a store. While easy to implement, it can lead to long waiting times if a large task arrives first. Shortest job. First scheduling prioritizes tasks with the smallest execution time. This minimizes average waiting time, but requires knowing how long each task will take, which is often impossible to predict accurately. Round-robin scheduling is one of the most important algorithms in modern operating systems. It divides CPU time into equal time slices, typically measured in milliseconds. Each task gets its fair share of processing time, preventing any single task from monopolizing the CPU. Here's how round-robin works in practice. Each process gets a time quantum, often 1 or 2 milliseconds. If a task doesn't complete within its time slice, it's preempted and moved to the back of the queue, allowing the next task to run. This creates fair, predictable scheduling. This process is called preemptive multitasking. When a task's time slice expires, the operating system forcibly stops it and switches to the next task. This ensures responsive system performance and prevents any single task from freezing the entire system. In ARM Cortex processors, the systic timer provides precise timing control for task scheduling. This hardware timer generates regular interrupts that trigger the operating system to switch between tasks, ensuring accurate time slice management and reliable multitasking performance. CPU task scheduling is essential for efficient system operation. Round-robin scheduling with preemptive multitasking ensures fair resource allocation and system responsiveness, while hardware timers like systic provide the precise timing needed for reliable task management. Real-time operating systems, or RTOS, are specialized systems where timing is absolutely critical. Unlike regular operating systems that prioritize throughput, RTOS must meet strict deadlines to prevent system crashes. In RTOS, tasks can be manually assigned specific execution times. Each task must complete within its allocated time slot to maintain system stability and prevent cascading failures. A task in RTOS is a small program or function that has its own dedicated stack memory. This stack stores local variables and function calls, providing temporary storage that prevents data loss when the system switches between tasks. Context switching is the critical process where the CPU switches from executing one task to another. This involves saving the current task's complete state and restoring the next task's state from memory. The context includes several critical components: the program counter, which tracks the next instruction, the stack pointer indicating the current stack position, general purpose registers holding temporary data, the link register for function returns, and the program status register containing system flags. RTOS uses two main types of memory strategically. SRAM provides fast access for the stack and temporary data during active execution. Flash memory stores programs permanently, and during execution, code is moved from flash to SRAM for maximum speed. During execution, the CPU follows a precise sequence. It fetches instructions from memory addresses, executes them, and increments the program counter to the next instruction. This process continues seamlessly as the RTOS manages task switching and maintains system timing requirements.